Section: Introduction. In this section, we explore how to evaluate the quality of text generated by language models. It has become challenging due to the wide range of text and tasks they cover. To tackle this, a method called language model-based evaluation has emerged. In this method, language models are asked to either give a score for quality, direct assessment, or choose the better option between two texts, pairwise ranking. Previous studies using private language models as evaluators have shown high agreement with human evaluations, as well as being faster and more cost-effective. However, relying on private models for evaluation has drawbacks like lack of transparency in training data, fairness issues, and high costs. To address these concerns, recent research has focused on creating open-access, transparent, and controllable evaluator language models. These open evaluator models, though, often struggle to match human judgments or private models' decisions, limiting their effectiveness. They are also inflexible, typically only trained for direct assessment or pairwise ranking based on general preferences like helpfulness and harmlessness. To bridge this gap, we propose combining direct assessment and pairwise ranking into a unified evaluator language model. By merging the weights of two separate evaluator models trained on these formats, we create a robust unified evaluator model. Our approach outperforms models trained on a single format or jointly trained models. We introduce the Prometheus 2 models, which excel in both direct assessment and pairwise ranking evaluations. We also introduce a new feedback dataset called the Preference Collection, which includes diverse evaluation criteria beyond just helpfulness and harmlessness. By merging weights from models trained on different feedback datasets, we achieve high performance in both evaluation schemes. Additionally, we discuss the use of language models as judges to evaluate text generation capabilities. Traditional metrics like Rouge, Blue, and BERT score may miss good quality responses that differ from a reference answer. Using language models for evaluation offers more depth and granularity similar to human evaluation. However, open evaluator models currently lack flexibility and show weaker performance compared to private models. Our work aims to address this gap with the Prometheus 2 models. We also explore the concept of weight merging, which has shown performance improvements in various domains. By merging models trained on different assessment formats, we aim to enhance the evaluation capabilities of open evaluator models to match those of private models. Section Summary. In this section, we explore the challenges in evaluating language model outputs and the emergence of language model-based evaluation paradigms like direct assessment and pairwise ranking. While prior works using proprietary LMs for evaluation have shown high correlations with human judgments, concerns about transparency and flexibility persist. To address these issues, we propose a unified evaluator LM by merging weights from separate direct assessment and pairwise ranking evaluator LMs, resulting in Prometheus 2 models that outperform existing open evaluator LMs on various benchmarks. Section: Methodology. In this section, we introduce a new approach for training a unified evaluator LM by combining the weights of models trained for direct assessment and pairwise ranking. We first provide background information on direct assessment and pairwise ranking for evaluator LMs, followed by explaining how we construct our training data. Finally, we describe our methods for training the advanced evaluator LM, Prometheus 2 models. Direct assessment involves mapping an instruction and response to a numerical score, typically using a Likert scale from 1 to 5. Previous studies have suggested various techniques to align the scores generated by evaluator LMs with human-assigned scores. For example, adding a reference answer as input to the evaluator LM and prompting the model to provide verbal feedback before assigning a score have been shown to improve the correlation between the model's scores and human scores. Additionally, integrating evaluation criteria allows users to customize the assessment standards based on specific needs. Pairwise ranking entails comparing two responses to an instruction and determining which one is preferred. Similar to direct assessment, incorporating a reference answer and verbal feedback into the evaluation process is crucial, We are the first to explore fine-grained evaluation in pairwise ranking settings, where evaluation criteria do not include descriptions for each score but focus on the criterion itself. Verbal feedback in pairwise ranking compares the similarities and differences between responses concerning the evaluation criterion. To create an evaluator LM that reflects user preferences, we develop the preference collection, which includes 1,000 evaluation criteria. We modify the existing feedback collection by pairing responses and generating new verbal feedback for each pair using GPT-41106. The resulting dataset statistics are presented in a table along with the feedback collection. Prompting involves querying an LM to make evaluations without training on feedback data. Single-format training trains a base model on either direct assessment or pairwise ranking feedback datasets, while joint training trains the model on both formats to enable cross-format functionality. Weight merging combines models trained on direct assessment and pairwise ranking datasets to create the final evaluator LM. We experiment with different merging techniques and find that certain approaches work best with specific base models. Section Summary. In this section, we propose a novel approach to train a unified evaluator LM by combining the weights of models trained for direct assessment and pairwise ranking. We introduce the methodology for direct assessment and pairwise ranking for evaluator LMs, discuss the construction process of our training data, and present the methods used to train the state-of-the-art evaluator LM, Prometheus 2 models. By merging the weights of models trained for different evaluation formats, we aim to create a versatile evaluator LM that can effectively assess responses based on user-defined criteria and feedback. Section: Experimental Setup. In this section, we will explain our experimental setup for evaluating evaluator LMs. We will start by discussing the benchmarks and metrics we use, as well as the baselines for our evaluator LMs. When it comes to benchmarks and metrics, we have several direct assessment benchmarks such as Vicuña Bench, Mount Bench, Flask, and Feedback Bench. These benchmarks include test prompts, score rubrics, and responses from various models like WIZARDLM13B and GPT-3.5 TURB00613. Additionally, we have pairwise ranking benchmarks like HHH alignment and AutoJ eval, where response pairs are judged by human evaluators. In our evaluations, we use metrics like Pearson, Spearman, and Kendall-Tau for direct assessment to measure scoring correlations against reference evaluators. For pairwise ranking, we use accuracy to measure agreement between evaluator LMs and humans. We also handle cases where responses are scored as ties by either excluding them for pairwise ranking evaluations or grouping them for direct assessment. Moving on to our prompting baselines, we utilize models like Llama 2 Chat 7, 13, 70B and Mixtral 8x7B Instruct v0.1. We also include proprietary LMs such as GPT 3.5 Turbo 0613 and GPT 41106 for comparison purposes. For single-format trained evaluator LMs, we test models like Prometheus 7, 13B for direct assessment and ULTRARM13B for pairwise ranking. We also evaluate Mistral 7B Instruct v0.2 and Mixtral 8x7B Instruct v0.1 on either direct assessment or pairwise ranking. In the case of jointly trained evaluator LMs, we assess the performance of AutoJ. Additionally, we look at Mistral 7B and Mixtral 8x7B when jointly trained for both direct assessment and pairwise ranking. Section Summary. In this section, we detail our experimental setup for evaluating evaluator LMs by explaining the benchmarks, metrics used, and the baselines employed. We utilize various benchmarks like Vicuña Bench, Mount Bench, Flask, and Feedback Bench, each with specific test prompts, score rubrics, and responses from different LMs. We also assess single-format trained evaluator LMs such as Prometheus 7, 13B, ULTRARM13B, and PAIRRM 0.4B, as well as jointly trained evaluator LMs like AutoJ, Mistral 7B, and Mixtral 8x7b on both direct assessment and pairwise ranking tasks. Section: Weight Merging. In this section, we will discuss the results of our weight merging method using Prometheus 2 models as baselines. The details of the training hyperparameters and prompt templates can be found in the appendix. When looking at the direct assessment results, we see strong correlations between the scoring decisions of Prometheus 2 models, GPT-41106, Claude 3 Opus, and human evaluators, with Pearson correlations consistently above 0.5. On the other hand, base LMs and single-format trained LMs show lower correlations with these benchmarks, mostly below 0.5. Prometheus 2 models outperform Prometheus and AutoJ by at least 0.2 units across benchmarks in their correlation with proprietary LMs. Notably, Prometheus 2-8x7b achieves a higher correlation with humans on the Flask benchmark compared to previous models, effectively reducing the performance gap. In terms of pairwise ranking results, Prometheus 2 models consistently achieve the highest scores across all benchmarks, indicating their ability to simulate human judgments effectively. Training a large LM like Mixtral 8x7b with feedback data proves to be a successful strategy in obtaining a robust evaluator LM that can generalize beyond its training data. Additionally, Prometheus 2 models significantly reduce the performance gap with proprietary LMs on out-of-domain test sets. Consistency across evaluation formats is crucial for evaluator LMs. Our experiment shows that Prometheus 2 models demonstrate lower performance differences across evaluation formats, highlighting their robustness. When comparing weight merging with joint training, we find that weight merging leads to superior performance compared to joint training and single-format training. This positive task transfer is evident in the improved direct assessment performance achieved through merging pairwise ranking evaluator LM weights. Regarding the effectiveness of weight merging, we conducted an ablation experiment to investigate if ensembling multiple models plays a role. Surprisingly, merging evaluator LMs trained on the same evaluation format does not necessarily improve performance. However, merging evaluator LMs trained on different evaluation formats leads to superior performance, indicating that the positive task transfer from weight merging stems from unifying different evaluation formats rather than ensembling multiple models. Section Summary. In this section, we compare the effectiveness of weight merging and joint training for training evaluator language models. Surprisingly, we find that evaluator LMs trained via weight merging outperform both jointly trained and single-format trained evaluator LMs, indicating positive task transfer. Additionally, our experiments suggest that the effectiveness of weight merging is not solely due to model ensembling, but rather from unifying different evaluation formats to achieve superior performance. Section: Quantifying positive transfer across evaluation formats. In this section, we investigate how training on direct assessment feedback data impacts pairwise ranking accuracy and vice versa. We conduct experiments by adjusting the alpha value in linear merging and assess the overall performance using all 8 benchmarks. To visualize the average performance, we scale the direct assessment Pearson correlations, ranging from 0 to 1, by multiplying them by 100 before averaging with pairwise ranking accuracy. The results are depicted in a figure. For direct assessment benchmarks, we observe that evaluator LMs achieve the best performance when alpha is set to 0.5, suggesting an equal contribution from both pairwise ranking and direct assessment feedback data. On the contrary, for pairwise ranking benchmarks, the optimal performance occurs when alpha is set to 0.3. This indicates that while both methods benefit each other, training on pairwise ranking leads to a more significant improvement in direct assessment performance compared to the reverse scenario.